Okay, so for today we are going to finish up this unit, and then we're going to do solving problems that deals with exponential function mostly. Before we start our lesson, I just want to go over the different formulas that we use with exponential function and when to use which one. Okay, so we're going to start with a quick review about exponential, and then we'll move on to our lesson. So the formulas that you have seen, probably, they look like this. So if you have A equal P1 plus R to the power of I, that's, 1 plus I to the power of N. That's one of the formulas that you probably have seen, or we have seen in one of our examples, right? And this is mostly used when we have money. We use it with a principal and a. But we can write that same formula in different ways, and it means the same thing. Okay? So we usually use this as this is the final amount. We use this as the initial amount, which is your principal. And then this is the rate. And this is the period. Okay, so how many times the years, or how many months, or whatever. Okay, so according to this, I'm gonna use a formula that's similar to this, but using different letters. Okay, but at the end of the day, no matter what the letters are, it's exactly the same thing. Okay, so if I use A equals A0, 1 plus I to the power of X or N or whatever it is. That still looks exactly the same thing, no? Except I changed my letter P to letter A0. It's exactly the same thing. Even if I used, instead of A, I use the letter Y. And instead of X, instead of N, I use the letter X. I'm still talking, it's still the same formula. Okay? As long as you know what goes where, you should be able to use these formulas. Okay? Now, what I need you to know is, let's just stick with one of the formulas. Let me see which one is in the formula sheet, and I'll stick with that. So this way it's easier for you when you're looking at your formula sheet. Okay, it's not in here. They only use the A plus. Okay. So let's use this formula. Okay. So again, A is your final amount. Okay. A0 is your initial, what you're starting with. I is your rate, so that's your percentage in decimal, and N is the period or the number of years or the number of months or whatever it is. We call this an exponential growth. Okay? So anytime something is increasing exponentially, this is the formula we use. For an exponential decay formula, so when we are decreasing, you guys should know this from the previous year. Right? Again, I probably use different letters, but it doesn't matter what letters we use, it's the same idea. So with the exponential decay, it's a equals a naught, 1 minus I to the power of n. Right? Still, I'm talking about the same letters. A is your final, a naught is your initial, the rate, and the period. But I'm talking about here exponential decay. So you are using up the money. So for example, if we're talking about depreciation value of a car, when you buy a car, right, you pay $20,000 for it. Every year it's going to lose 10% or whatever. I'm talking about this example. It's an exponential decay. Okay, so it depends on what the question is asking you. You need to pick one of these two formulas so far. Okay, in this case, they have to give you a rate. If they don't give you a rate, you can't use this formula. The other two formulas that I want to mention, they are the half-life and the doubling time. Okay, and again, these are your special case formulas. So if the question says half-life, then you know you use the half-life formula. I'm going to talk about that. And if the question says it doubles every whatever, we're going to use that formula. So the two formulas for the half-life and the double, I use this version because that's the one I give you on the test. Again, we can use any letter for A and A naught. It could be like Y equals to P, whatever, right? It doesn't matter what letter you use, it's the same idea. So this is for half-life. Okay. Again, this is your final amount. This is your initial amount. The reason why this is called half-life, because your base is 0.5. 0.5 is a half. Okay, so that's your base, and that's why it's called half-life. T is the time, and H is the half-life time. So let's say we have this example. So let's say you have a bacteria count. Let's say you have 1,000 bacteria. Okay, and you gave the bacteria antibiotic. Let's say in your blood count or whatever, there's 1,000 count of bacteria. I know the numbers don't make sense right now, but just let's just use that example. And then you're taking a dose of bacteria every half an hour. The bacteria count is halved every 5 hours. How many bacteria will be remaining after 24 hours? Okay, so this is an example of a half-life. How do I know it's half-life? It's just because it says is halved right there, right? So this is where I know I'm going to have to use the half-life formula. So out of this information, what do I know? The initial count is what? 1,000. So my initial is 1,000, which is A0. Okay. What else do I know? What time? 24 hours, that represents T, right? What else do I know? So, this is very important. When it says it's half every 5 hours, that means this is your half-life time. So every 5 hours, you're going to lose half of the amount. Okay? So that means this represents the H letter. So the half-life time is 5 hours. What am I looking for? This is not on your notes. What am I looking for? The final amount. So I'm looking for A. Okay, I don't know what A is. So let's write the formula. So I have A equals 1,000.5 to the power of 24 over 5. So you see that A0 is 1,000. That's my initial amount, 0.5 because it's halved. T is I'm looking after 24 hours, so that's T. And then H is my half-life time. And I can put that in the calculator and I can get how many I have left after 24 hours. So it looks like there's about 36. Okay, so this is an example of half-life. And the other formula that we're also going to look at, so far we looked at the two rate formulas, the decay and the growth. We're looking at the half-life. There's one more formula that we're going to look at, and it's the doubling formula, which is A equal A0 doubling. So my base is 2, T over D. Now we're just changing the letter. Again, this is my final. This is my initial. It's doubling, so that's why my base is 2. This is the time. And this is the doubling life. So let's say if it doubles every month, then D is 1 month. Okay? And this is basically, what did I say? This is called the doubling. Okay? Make sure you remember these formulas. Make sure you know these formulas. Okay? Because you're going to have to be able to use them depending on the question. Okay, now this is done in the grade 11 stuff. This is just a review from the grade 11. We're going to have to look at how can we use that right now in what we're doing. Remember that we're solving equations, okay? So are you guys ready for me to move on to the next page? Okay, so we're going to recap a couple of things as well. So the goal for this lesson is to model and solve real-world application in exponential growth and decay. So the exponential relations are modeled by the exponential equation y equals a b to the power of x. So this is the general formula that we use for exponential, regardless of what the value of b is. What does a represent in this case? That's your initial. And b is your base, but what do we call it? It's an exponential. It's sorry, I'm just going to write something else. We're going to call it decay or growth factor. Okay? If B is greater than 1, then it models growth or decay? Growth. And if B is less than 1, then it models decay. Okay? So remember, guys, no matter what the question is, if I have, for example, a percent rate, right? So if I have the money question that we had before, and we say like you started with $2,000, let's say, and then it's increasing by 5% annually, right? Let's say I have this. If I actually do you don't have to write this example. If I actually do inside my bracket, it's going to be 1.05 to the power of x. So if you look at it, yes, I started with an equation that looks like this. Right? I started with an example that looks like this, but I ended up, after I plug in all my information, I ended up with an example that has y equals a b power of x, right? So after I do my addition, it's going to end up looking like this when I do my simplification, okay? So yes, I have 4 different formulas, but at the end they're gonna simplify to something that looks like this. Let's look at this example. So a city's population can be modeled by the equation P equals to 1.4 to the power of times 1.045415 to the power of t, where P represents the population in millions, t years after 1985. In which year did the population first exceed 3 million? What am I looking for? I'm looking for time. And how do we know that? In which year? So it's asking you for a time. Okay? Good. So I'm looking for time. What do I know? I know my initial population, which is what? 1.4. So if I look at my example right here, at my equation, this is my A value, which is 1.4 million. Okay? What else do I know? Yeah, we'll get to that in a second. What else do I know? Do I know my ending population? What is it? 3 million. The question is asking you, in which year did the population first exceed 3 million? They have to give you, because you have only 2 unknowns. Eyes on the board for a second. You have 2 unknowns. You have P and T. In order to solve one, you need to know the other. Okay? That's the rule of solving equations. You have to give me 1 so I can find the rest. So if they want you to solve for T, they have to give you P. And in this case, they gave you P to be 3 million. So this is my ending population. Now, at what rate is the population growing?
1.04.
Okay. This 1.0415, that's your factor and not your rate. So there's 2 different things. We're talking about factor and rate. Remember, what is the formula for growth? Exponential growth. What's the formula for? So it's A equals to A0, 1 plus I to the power of N or T or whatever you want to call the letters. Again, they're letters, right? It could be whatever letter you want it to be. The question is asking you for the rate. The rate is the I. Okay? Now, 1 plus I gives you 1.0415 now. If I want to look for I, what do? Subtract 1. So if I have 1 plus I equals to 1.0415, right? To solve for I, I'm going to have to bring the 1 over. So that's going to be I equals 1.0415 minus 1, which is 0.0415. Now remember, rate has to be in percent. So what do I do to find in percent? Multiply by 100, and that should be 4.15%. Okay? So you have to be careful with the terminology that they use. Okay? And you have to remember that rate is percent, while the growth factor is the actual 1 plus the rate. Okay. So let's see what happens. I know that P is 3, and I know that I have this. What do you want to do to solve for T? Huh?
Isolate.
Isolate. How do you isolate?
Take it to the denominator.
Make
Take
the
what?
bases the same.
Make the bases the same. Before I do that, this is very, 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 very important. Okay?
Fraction.
So, first thing you want to do is you want to get rid of that multiplication that's happening here. The 1.4 times the bracket, you want to get rid of that. So if I want to get rid of that 1.4, I bring it over, and it's going to be 3 divided by 1.4. And that gives me 2.14286. Leave as many decimal places as you can. Now, Eric, you said something. You said that if I want to solve for my exponent, I have to
Isolate.
isolate by making them
Oh, right, the bases.
same base. Now, we are used to doing same base, but we're not used to making same base with decimals like this, right? We are, if it was like 32, yes, and base of 2, you can do that, okay? But with decimals, we're not used to that.
Fractions.
Fractions, we can't put that in fractions. We don't know what it is. What does it say here?
Use trial and error.
Use trial and error. So for now, we're going to just use trial and error, and then I'll teach you a simpler way. It's not in your curriculum, so I don't expect you to know it, but it makes your life easier. Okay? Trial and error is part of your curriculum, so you should know how to do that. So trial and error means try values for t until you find the answer. That's what it means. Okay? So what do you want to plug in for t? Give me values. Let's start. 2. So can you find what would it be if you're going to do to the power of 2?
It'd be 1.084.
So it's way far from 2.14, no? Okay, so it's not 2. What else? Give me another value.
3.
I would make it bigger because you see it only moved up by 0.0 whatever, right? Very small. 7? Okay, try 7. What do you get? I'm waiting. 1.329. Also still far from 2.14. Give me another value.
I went 22 and it was 2.4462.
22,
Yeah.
2.4462.
Yeah.
So that's too high, right? Because I want 2.414. So it has to be lower than 22. We know that. 20? Okay, let's try 20.
20 was 2.2552.
2 point.
2552.
So still lower than 20 because that's still too high. Go 16. 18?
Yeah.
18? You want to do 18? Okay, what do you get for 18?
2.0790.
Okay, so we're getting close. It's lower, but we're getting close. So let's try 19 because we tried 20, we tried 18. Let's try 19. What do you get for 19?
2.1653.
2.1. So it's somewhere 2.16 what?
53.
53. So we see that it's somewhere between 18 and 19 years. Okay? Because we're exceeding 3 million, we're going to have to go with this. Okay? So we know it's somewhere between 18 and 19 years. Okay? Why? Because it's 2.14. That's what should my answer be. I got 2.079 if I put 18, and I got 2.1653 if I got 19. Okay? So it's somewhere between 18 and 19 years. We're going to go back here. The question is, in which year did the population first exceed 3 million? So how would I know in which year? If I know it's 18 years or in 19 years, how would I know in which year is that?
You add up.
To what?
1985.
To your 1985, right? Because the equation is made as of 1985 is your year 0. Okay? So if I want to write my therefore statement, therefore, what would it be? 1985 plus 19 is what? 2004. Okay? So in 2004, the population exceeded 3 million.